Hello, my name is Alan Folmsby, and the subject for today is diamagnetism and paramagnetism. So first I'll just give the simple explanation of diamagnetism is very weak repulsion of objects away from a bar magnet, for example. Paramagnetism is a very weak attraction towards a bar magnet. And for example, if you put a north pole next to a diamagnet, it'll get repelled away. But if you put a south pole next to a diamagnet, it'll get repelled away. But the paramagnet's a stronger kind of magnetism, even though it's weak. You've all seen iron magnets, the ferromagnets, and how strong they are. Paramagnets are extremely weak, although they're stronger than the diamagnet. Now, if you take a North Pole iron bar magnet and you put it next to a paramagnet, it'll be attracted to the North Pole weakly. But if you put a South Pole of the bar magnet next to the paramagnet, it'll be attracted weakly to the bar magnet. As opposed to two bar magnets where they would have a repulsion or attraction. Diamagnets, for example, just repel any kind of external field. So as examples, I'm going to be talking about hydrogen and lithium. And now, the conclusion I'm going to be getting to towards the middle and end is that there's a time-like dimension involving atoms, and there are some space-like dimensions involving atoms. And diamagnets have a loop of the time-like, so it repels. And the paramagnetic elements have loops involving more of the space-like dimensions, and so that will attract, like wings. And I'll be explaining in more detail using models for you in just a few minutes. The theory is not approved by educators. This is not standard science. If you wanted the standard answer for diamagnetism, you could say conservation of energy makes hydrogen diamagnetic, and that you can prove with the Hamiltonian that Schrodinger's equation is consistent with the conservation of energy. And that's what the standard science might have available. Or if you wanted more detail than that, they could say that it's quantum field theory, which you wouldn't understand. Now, what I'm proposing here is a geometric reasoning, not algebra. And this theory I'm proposing is a small geometry for diamagnetism. And I can also propose a larger geometry theory for paramagnetism. And I'm using this instead of the Hamiltonian lumped functional algebra. And I'm just going to click on this. Oh, there it goes. So I'm going to be talking about hydrogen and this molecule. And as the earlier lectures I've given, I'm using the 8-dimensional physics. But I'll review it for you briefly in case you haven't seen the earlier videos. As you know, there's 4 dimensions: time, x, y, and z. So that's dimensions 1, 2, 3, 4. Now there's also dimension 5, 6, 7, 8, which is magnet time and magnet space, x, y, and z. So these are labeled, and then electrons could be a frame of reference, and then magnet time comes out of electrons, and magnet space goes into electrons from protons. Now, from my notebook number 12, I've put together some sketches here you can see in which there's a hydrogen diamagnetic molecule on the left, and on the right there's lithium. It's a paramagnetic element. And this basically shows that the molecule has 2 protons on the left for H2, and there are 3 dimensions, the 5, 6, and 7 dimensions, and the red is the magnetime. And you see that that overlap then will make that loop for diamagnetic elements. Now, taking away all the excess sketch there, you see that loop, and that an external field, when hitting that loop of magnetime, will cause it to be repelled because it's an anti-vortex. Whereas on the right, when we take away things and show only the space-like dimensions, there's something of like little wings coming off the nucleus, and which these will be attracted, since these loops are using space-like dimensions. And another close-up, this is showing the hydrogen diamagnetic representation, and it's like a flat sub-universe. And there's only 2 space dimensions, so it's a flat sub-universe in which you can look at from this point of view, where magnetime looks orderly, or you could look at it from our universal view on the right here, in which this hydrogen molecule H2 is bonded by a twisting, like 2 ropes twisting around each other in what we've seen before. And as I showed in earlier types of videos, for example, if we had a red rope for the bottom proton and electron, and then a yellow tape coming from the top proton down to a weight, that would be the electron. So I'm going to show you what that experiment looked like. So what you're seeing there is that yellow tape hanging down, which represents the top proton and the bottom electron. And then the red rope was the bottom proton and the top electron. And they're wrapping around each other using the non-crossing law. And this is also affecting diamagnetism, in which these areas are important for reality. These are the kind of details I'm presenting so that you can make progress beyond this lumped functional energy considerations. This is a finer level of detail. And here's the final slide from my notebook here, the paramagnetic geometry of a propeller shape in lithium. The nucleus is those 3 black circles there, and then there's 3 electrons in red, with showing those black lines and arrows of the dimensions, magna space coming out of the protons and into the electron. And then generally all the space-like then has a hydrodynamic effect like a sailboat kind of. But I'm going to show you some small models now that I put like a sculpture. I'll just turn the camera around. Okay, almost ready. I'm getting it ready now. All right, so there we can see the little model. I'm going to get a drink for a minute. Okay, now I'm back onto the microphone right in front of the sculpture here. So I'm going to grab a hold of that sculpture, and so this would represent 2 hydrogen atoms. The white proton with the P on it and the brown electrons are connected by 3 wires, which is the 3 dimensions. which I call HX, HY, and magnaspace, or magnetime. All right, so I got my mobile microphone in my hand. I'm walking over, shaking the floor. All right, so here's one hydrogen atom here with the proton in white and electron in brown, and it's connected with 3 dimensions. You can see as I rotate it in 3 dimensions how the 2 flat dimensions, there's a red one for the magnetime, and the black one and white one is for the HX and HY, magnaspace. Now, on the other hydrogen model, I put this spin membrane in there to show you that the spin of this is counterclockwise on there. And as you put together 2 atoms, it forms a molecule, so the spins are the same direction. All right, so as the red overlaps the red anyway, this would be both of them spinning the same direction. So that that anti-vortex of the red magnaspace overlapping the red magnaspace wire there, this is what repels the external B field on any test. Now, in a minute, I'm going to give you great detail of what the external B field is, because that's just as important as the target of the B field. How did you make an external B field that's going to repel this anti-vortex? And I'm going to be showing you that in about 10 seconds. Now, this sketch here shows, say, a NMR experiment, nuclear magnetic resonance. So you have a bar magnet on the left, and there's a different bar magnet on the right. And there's a little glass thing in the center where it's a B field is being imposed on the glass sample of NMR experiment. And you see that there's motion. There's the iron ring on the left, as I've shown in earlier lectures. Iron has 2 rings of protons on the left, and another atom has 2 rings of protons on the right. And they're both going the same way, so that one looks north and one seems to be the south, from perspective of the sample glass in the middle. So that there's a sweeping of all these lines of connection to electrons and protons. For example, on the left, there's a black ring current of those 12 protons, and those are connected to the electrons on the right bar magnet. And the protons on the right bar magnet, you see, are connected by lines to electrons on the left bar magnet. This is how magnets work. They're like extended atoms where the nucleus is on one bar magnet, but the electrons are on the other bar magnet. This is essential for modern science to admit that this pairing is deterministic, and the flatness of these membranes allows the magnetic induction to occur for diamagnets and paramagnets. So here's a list of the paramagnetic elements: lithium, oxygen, sodium. And what you find, platinum, is that these are pretty much on the left side of the periodic table. And that if you look at the periodic table, you find that, see how I've divided the left and right halves here in terms of a split down the middle. The cube 4 is on the left and the cube 3 is on the right. And this also happens to be the paramagnets mostly on the left, and the diamagnets are mostly on the right. So in other words, the top row, the top period, helium, these are diamagnetic. Now the second row, period 2, let's see, only oxygen is paramagnetic. and lithium is paramagnetic. Those are on the left side of that split. Now, going down to the third row in the periodic table, we could magnify that a lot more over on the camera. All right, so we can see that the row with lithium and oxygen there, those are the only two paramagnetics there. They're on the left side of the split. And the next row down, sodium through manganese, or through phosphorus, those are all paramagnetic. Well, I have the list right here. I've already got them circled. Let's see. See on the top left, I've got the paramagnetics all circled. And on the right side, these are all diamagnetic. The top right, there's 8 on the right. Say like from krypton to the left, there's 8 in a row. They're diamagnetic. And then below that, xenon, there's 8 more. They're all diamagnetic. And you see the paramagnetics are on the left side of the periodic table. They're all circled. And the diamagnetics are mostly on the last 8 on the right side of the periodic table. And that's true for several periods until you get to the last row there, when there's 24 diamagnetics in a row. And the left ones here circled are paramagnetic. So there is, what I'm proposing is that this is all about hydrodynamics, the shape of those fins sticking out from the orbitals, and all the bonding in which the paramagnetic will have large areas. They're unsymmetrical, that are causing the attraction. But the diamagnetics all have bonds like hydrogen, in which these loops of the time-like dimension are available on every element. So that's just a little weak repulsion of magnetic fields. Okay, I've got the right buttons pushed here. Now, I want to spend some time more on this B field, because a lot of textbooks tell you that we're going to apply an external B field and it's a uniform magnetic flux we're going to apply to our experiment, as if a B field is anything more than just electrons and protons moving relative to each other. No, it is. It's just quantized lines between copper, say you had a copper electromagnet, and protons in there have lines connected to electrons in a different copper coil. So it's not like a gallon of milk. It's all quantized into lines of flux and with non-crossing laws. And with that in mind, we can look at the standard units of measure. The Tesla is the B field, the magnetic flux density. That's the number of Webers per square meter. Now, a Weber is defined on the third line here. It's the lines of flux per second passing through a space. And a line of flux is a line drawn between a proton and an electron. That's a line. And that line has 3 dimensions, as I was pointing out in that little model there. So each line of flux has 3 dimensions, one of which is time-like. But since they're moving through space, that is also time going on, action during time. So at the bottom line here in this, time and time-like action both are in a steady B field. So when people talk about, quote, an external B field is applied, unquote, to your experiment, that's action. There's something moving. It's combing. All the little lines are being combed. And the event is invisible, and it's affecting spin unpaired electrons. So spin unpaired, I'm making a distinction between pairing electrons and protons with a different thing, which is spin unpaired. So the spin of one electron is different than the spin of another electron. And it's an event of the magnetic flux density sweeping and combing through lots of lines in atoms. And the B field is events per second. So basically, in units of measure, this is accurate, per second. That's B is equal to second to the -1 power. And event is the exclusion of dimensions 5, 6, and 7 for ions and atoms. And this will be able to gather unpaired lines, but orbiting electrons slip by 2 by 2. So electrons that are bonded with each other are not going to get picked up by the external B field. They will not get gathered into a vortex by it. They will slip by. It's only the unpaired electrons. So that's why I want to define some terminology here. This is 4 words about motion of magnetism: spin, eddy, orbit, and combing motions. First, the spin. There's only 2 choices. Like in that wire model I showed you, there's HX and magnetime, TH. That's spinning one way. Or the HY, black wire, and the magnetime, TH, in red wire. Those are the 2 choices. And I've explained this in earlier lectures, so I'm not going to show you too much about that. Now, so the spin is in each line. So a line connecting a proton to an electron has these 3 dimensions, and that has 2 spins that can be observed. Now, an eddy is the tracking of lines from a proton current. So like in iron, where there's a proton current in the nucleus, the eddy current is electrons going in a circle, and lines are connecting the proton current to the electron current, and that tracking, that makes a vortex. So the vortex is an eddy current with all the lines attached to it. Now, an orbit is when 2 lines tangle. So say we have like one hydrogen atom with one line and another hydrogen atom with another line. And if they tangle up like in that video, then that's an orbit. Look, it's orbiting. It's an orbital. Weight is an electron. The red is another line. So those are orbiting electrons. That's an orbital. You can define the quantum numbers, n, etc. N is the number of times it wraps around the other line. And so the last word is comb. This is combing, so that a sieve, it's like a sieve passing by flat subuniverses, and it's pushing around things. Now the comb will gather and sweep these lines into a vortex. If their spin is not paired off with another spin, this vortex is formed out of gathering together local lines across space. And this magnetime will grow in a big arc across space, like you've seen on the sun, how magnetic lines grow. That's the magnetime growing, like in the previous lecture on the magnetic vortex. And one thing that goes on, the loyalty changes in the vortex. So the pairing of one proton-electron is a loyalty. And yet that can change, where now the electron will move along and become paired with a different proton. And that could be an ohmic energy loss there. And I'm trying to show that the bar magnets and electromagnets are the same by talking about this. loyalty change here. So let's see, I just have one more thing I could show you on the camera over here. Hold on. All right, I moved the camera. All right, I moved the camera over to the giant screen of stuff here. And so let's see, I got some more notes here. Now, just to summarize and make a conclusion here, to reiterate on diamagnetism and paramagnetism, the weak repulsion of diamagnetic materials is because of the dimension I call magnetime is forming a loop in that molecule. And that will repel a north pole, and it'll repel because time goes the opposite direction as space. And your external B field is space-like flat subuniverses. Now, paramagnetism is a weak attraction, but stronger than diamagnetism, because larger areas are involved in the space-like dimensions of atomic bonds and unpaired ion bonds and just lines of flux. And that diamagnetism is not depending on temperature, but paramagnetism is more dependent on temperature and gets weaker at higher temperatures. And diamagnetism is really unaffected even near absolute zero, like gravity. If you go down to 1 degree Kelvin and gravity is the same, very weak. Now, if you take diamagnetism, it's the same at 1 degree Kelvin as at room temperature for a material, and it's very weak, like gravity. I suspect they're related. So I described the four terms, spin, eddy currents, orbits and orbitals, and the B field is a combing mechanism, and the spin of each line. So when I'm talking about line of flux, that means there's 3 dimensions in that line, 2 space dimensions and 1 counterflowing time-like dimension. And that provides local torque available for radio waves, for example. Now, I had an earlier thing about radio is not photons. And in that, I talk about the local torque that is necessary to propagate radio to a partial vacuum. And the orbit uses 2 lines. So a bond can have orbiting 2 lines together, 2 electrons on 2 lines orbiting each other, just like a rope orbits another rope because of the non-crossing law. And the B field is combing things, and let's see, I'm at the end of my tether here. Oh, there it is. I was able to get the bottom of this picture into view here. So anyway, I'm saying that a bar magnet is just like a solenoid electromagnet. And then if you take a bar magnet and put it inside of an electromagnet, they have relative velocities in the flux cores of this combination iron bar magnet inside of a solenoid. And so you get the amplification, the great increase in magnetism by having the iron core, because the relative velocities, the sweeping of the outer magnetic field of the copper coil is the frame of reference in which the motion of the proton current is going. So they're adding together. And the electron is quite linear. As I explained before, it adds up the 2 space dimensions to sum the time dimension going the other way. I showed you the paramagnetic elements on the periodic table, and how 8 elements on the right side of periods 4, 5, and 6 are all diamagnetic. Only 8 elements on the right. And then in period 7 of the periodic table, they're all diamagnetic for the right 24. So I explained the 2 things according to future science. Now, in conclusion, you can take my word for it, or you can use the conservation of energy to say how hydrogen repels because of the conservation of energy. And lithium attracts, of course, because of the conservation of energy. No, there's a finer level of detail I provided. Thank you very much. My name's Alan Folmsby. Goodbye. Bye. Bye.